Welcome, chemistry students, to Tuesday, April 7th, our second week of e-learning. Today we're going to be reviewing how to illustrate single displacement or single replacement reactions. This is a topic that we discussed before spring break, but that is now a long time ago, so we'll go back over it today. We're going to go over the first page of our 8-13I notes, and then you will complete the rest of this note packet after our discussion. The answer key is on Google Classroom, so don't hesitate to consult the answer key. If you have any questions as you work through completing the note packet, don't hesitate to email me your question. And if the majority of the students or whatever have a concern or question about that problem, additional videos can be made for 8-13I. Single displacement reactions or replacement reactions involve two types of things in general happening. One type of thing is an active metal replacing a less active metal in solution. They can also occur when an active nonmetal replaces a less active nonmetal in solution. The example we're going to deal with first is an active metal replacing a less active metal. Recall that an active metal just means that it is better at forcing its electrons on other metals. Active metals can force their electrons onto a less active metal. That less active metal in solution has a charge initially, but when the more active metal forces electrons onto it, the less active metal loses its charge, so there would be nothing to hold it in solution. The reaction we're going to take a look at in this an example is the very active sodium displacing the slightly less active aluminum from solution. In this container right over here, we see sodium atoms being dropped into a solution containing aluminum, which is 3+, and 3 nitrate ions. So there's 3 sodiums being dropped into a solution of aluminum nitrate. Again, aqueous means that it is in solution, that water has pulled the aluminum off the nitrate ions, and they're flowing freely throughout the solution. So once those sodium atoms are dropped in solution, sodium is more active. So each of those sodiums are going to force that aluminum to take 3 electrons, one from each of the sodiums. Aluminum's charge, as you recall, it is 3+. It is in family Roman 3. So it initially lost 3 electrons, and now the sodiums are going to force 3 electrons back onto it, causing the aluminum to lose its charge. So in this portion, we now see the aluminum has the sodium's electrons. It is no longer charged, so water cannot hold it into solution, so it will precipitate. PPT is abbreviation for precipitate. It will precipitate out of solution. Now, sodiums are charged now, so they will be able to remain in solution. What did the nitrate ions do here in this reaction? Well, the nitrate ions are all minus in this container. They're all 1 minus in this container. They're all 1 minus in the first container. The nitrate ions have done absolutely nothing. For that reason, the nitrate ion is called the spectator ion. The spectator ion has no changes in charges. So our initial chemical equation, 3 sodiums were dropped into a solution containing a formula unit of aluminum nitrate, and when we're finished, we have the sodiums floating around with the nitrate. The abbreviation for floating around together is aqueous. But the sodiums are not actually attached to the nitrates in solution. And the aluminum right here is solid. You could write a PPT after it, or you could draw an arrow down showing that it precipitated from solution. An ionic equation is merely illustrating this same equation, but wherever there's an aqueous, you pull it apart. So we start with 3 sodiums. The aqueous here we replace by pulling the aluminum off. It's 3+. We know that because it's in family Roman 3. and there's a 3 subscript right here, which was crossed down. So we have aluminum 3 plus aqueous, and we have the 3 nitrate ions. The 3 goes in front. We have the 3 nitrate ions. When the reaction is over, we can see in this equation, in this container right here, we now have 3 sodium ions, and they are 1 plus each. We still have our 3 nitrate ions floating around. They're aqueous, and aluminum is no longer floating around. It precipitated out of solution. So the ionic equation is just a word for saying pull the salts apart that are floating around. To complete the net ionic equation, all we do is get rid of the spectator ion. In this equation right here, the 3 nitrate ions are there. They're 1 minus. The 3 nitrate ions are still 1 minus on the product side. We just cancel them out. So the overall change is we started with 3 sodiums with no charge and 1 aluminum with a 3 plus charge. And when we're finished, we have 3 sodiums with the 1 plus charge, and we have the aluminum no longer charged. It's back to neutral. Consult your notes that we took before spring break as you go on to complete the rest of this packet. The answer key for help in completing the rest of the packet is on Google Classroom. And again, if you have any questions on any of this, please email me that number. I can discuss that with you. If a significant number of students have questions on any of the same ones you do, additional help videos will be made. Thank you very much, and good luck with the assignment.